So hey everyone, today we are building a sentiment analysis model, which is a simple but very powerful project for basic understanding of ML models and neural networks. So let's get started. First of all, go to kaggle.com and in the search bar search for sentiment 140 and open the first link. You can see the name here by Chris, and just go ahead and click download and download the zip file here. Since I've already downloaded, I won't, but you can download the zip file here and extract it. You get the CSV file. You can open it in Excel and see how the tables are placed and oriented. You may or may not do that, no worries. And second step is go ahead and upload that CSV file in your Google Drive. You can create a folder named sentiment project, and inside that you can upload it, because we are going to upload every files inside this drive, and these are the files we'll be uploading later on after we have built the model. So don't worry about this, just upload the CSV file like this and name it anything you like. So now we'll go to Google Colab, which is our IDE for coding in Python, and we'll be using various libraries there for ML model development and ANN. Here, go ahead and create a new notebook. You can name it anything, and then create a cell from here or from here. And in our first cell, we will mount our Google Drive to our Google Colab, so we can use our CSV file anytime we'll want. And don't worry much about the code or syntaxes, because our primary focus for now is to learn how to clean texts, vectorize, and actually build the model. Okay, so also I will link these files with the videos, and I'll also attach a GitHub link, so you can always get the code whenever you want. So let's see our second cell. In our second cell, we have imported pandas.pd. This is a library, very important library in Python, and we have read our CSV file from the location of our drive. You can get your location from here and just paste it here, and it will read the CSV file and keep it in a data frame. So our entire data set will be in a data frame, and we'll be performing our operation on our data set using this data frame. Okay, and these lines are to avoid any errors and to tell the compiler what to expect. It's a very simple code, not much brainer. So this header equals to none means there are no titles or headings in the CSV file that we have just imported, and this gives the title to all the 6 columns in our CSV files. So in our third column, we have just seen the top 10 rows of our dataset, just to see how they are oriented and how they look. So these are the titles that we have just given earlier. And now let's see what is the shape of our data frame, what is the shape of our table here. So we use df.shape, and we can see here 1.6 million, 6, which means 1.6 million rows and 6 columns. We can also see here we have downloaded this CSV file with 1.6 million tweets. Okay, and then in our next cell, 800,000 tweets are labeled as 0 and 800,000 tweets are labeled as 4. So this is a perfectly balanced data set that we have. Our model might overfit or underfit, and our metrics like accuracy or something will also not be much reliable. Okay, so let's go to the next cell here. So what does this say is we will not be using 1.6 million rows entire tweets for now. We'll only take a sample, because that will be much for processing and much slower for computing. So we will just take a sample of 200,000 tweets. This is the new data frame with 200,000 tweets, and this random state 42 is just there so that every time we will run these cells, the 20,000 tweets will always remain the same, and the results will be reproducible. So after that we again check what is our shape of our data frame now, which is 20,000, 6, which is exactly what we need. So let's go ahead and see what our value counts is, as we did earlier, and we can see again it is nearly perfectly balanced, which is very good. So we can see here there are 9,000 and there are 10,000 positive and negative tweets. These are the labels, or say targets. So now we drop all the remaining columns and just we are left with text and target. That's all we need, and we see the top 5 rows of our dataset. As we can see here, we have only 2 columns now. That's all we need. And in our next cell we replaced 4 with 1. It's just for simplicity, so that now all the positive tweets are labeled as 1 and all the negative tweets are labeled as 0, and nothing much. So now that's all our setup for our data set. Now we will go for cleaning. As you can see here, the tweets are messy, very messy, and not processable, so we must clean them so as to see the sentiments they carry. So first of all, we will import our, so we import RE for regular expression and nltk for stop words. So what are stop words? Stop words are like the, or, is, am, are, which do not carry sentiment themselves. So we now, the stop words are already predefined, and this function now loads the stop words to our memory. And in our next cell we create a function called clean tweet text. This is the parameter we will receive. So any text will be received and it will go through this function and it will be cleaned. So how does this function work? Let's see. So text equal to text.lower, which is to lowercase everything, and next is to remove URLs from our text, which we will be accepting as a parameter. And next we remove all the mentions, we remove the hashtags. Tweets do contain this, so we have to remove this because they does not contain any sentiments within themselves. So next we remove punctuations and numbers, and next we use this method dot split to split the sentence into individual word, and then we use this for in loop to remove the stop words. So and we join the words back into a sentence. Now it was just the function creation. Now we actually call the function here. df text, which means the column here text. We can see here text, so we send this text from our data frame and apply this method called clean tweet, and this text is sent as parameter here and it is cleaned, and the final will be in our data frame set as clean text. And in our next column we just see the top 10 rows again, just to see how it looks. So text and clean text. So we can see here example @ is removed and all are lowercase. So you can see the example here. We would only need 2 columns here, clean text and our label. So we see the top 10 rows, and we can see here some are labeled as 0 and some are labeled as 1. Very earlier we can see just 0, 0, 0 because these are sorted, and all the remaining positive tweets, or say the tweets labeled as 1, are below. So our cleaning is done. It's the most important thing to be done in any type of data science tasks, because the real world data are always messy, and to analyze them and visualize them we must first clean them. But we used simple basic cleaning methods. we do have multiple options of cleaning, better ways of cleaning. So we know machine does not understand texts or languages, so we have to convert it to number. Machine only understand numbers. So so that process is called vectorization. So in this cell we can see that we have imported tf-idf vectorizer, which we will be using in our vectorization process from sklearn.feature-extraction.txt. So this process is also called feature extraction, as you can see. So vectorizer equals to, so we have used this function, and inside max features equals to 5000. So what does this mean? This means that from our entire data set, we will be extracting only 5000 words, 5000 important words, and based on those 5000 words, all the tweets will be converted to numbers. So how will that happen? That is a little complex process to understand, but we will. X equal to vectorizer.fit transform. So this is the actual process. I am drawing this data frame X, or say table X here, and how does it looks. So we have our 5000 features, or say 5000 extracted words in columns, and 20,000 tweets in rows. And these are also called toms, and these are called documents. So the name tf-idf vectorizer actually means tom frequency and inverse document frequency, tf-idf vectorizer. So these are toms and these are documents. So each tweets, say the tweet 1, so how do they get vectorized is based on these 5000 features. It forms a array, or say a tensor, or say simply a matrix, you can say, and based on this the entire tweet gets a score. Suppose this gets 0.8, these words get 0, other words get 0, some words get 0.6 or something like that, and therefore our tweet 1 is vectorized in the word, vectorized into numbers. And how do they get this score, this tf-idf score? It is pretty simple formula, but I will talk about this later in another video, I guess, because this video will be too complex and long for me to explain tf-idf vectorizer. Okay, and so on every tweet will get vectorized into numbers like this. So it becomes an array of 5000 elements basically. You can call it tensor or simply matrices, anything you want to call it, but it becomes like this, and 5000 obviously, and it is mainly sparse. So these are called sparse matrix, and sparsity is also a big thing to be handled, and it does have disadvantage, which we will talk about it later on. So let's go ahead and just see here. So y has the target, that is label, and x has the vectorized tweets. Vectorized means in numbers. So what does the tweet? So see, as we expected here, 20,000 rows and 5,000 columns. So yes, if we see the shape of our data frame X, then we can see 20,000 tweets and 5,000 data type, and 5,000 columns, and the next is just 20,000 rows. Just a single column, 20,000 rows and no columns, because it's just labels of zeros and ones. Okay, so let's go to the next cell here. So this we have vectorized already. Now let's split. We must split our training, our data set into training set and testing set. So we import train test is split from again sklearn, and then x train and y train, x test and y test, which means for training set that will for training set we have x and y, for testing set we have x and y, which is obviously cleaned vectorized text and target. So we just use this function here, train test is split simply on x comma y, and our test size will be 0.2, which means 20% of our dataset will be for testing purpose, and our 80% will be for training our model. And random state 42 is again just to make the results reproducible, and so that every time we run the cell, the 20% test size and 80% training data will always be same. Basically it is random but not random, you get it. So we just check the shape of our final splitted data, which is 16,000, 80% of 20,000, and columns remain 5,000, and our test size remains. So we are basically performing training on only on our 16,000 data. So let's go ahead and actually see what how to train the model. So we import logistic regression model from sklearn linear model. We are using logistic regression because it's simply for our binary classification whether the tweet is positive or negative. And so this is optional for now. If you need it, you can, but this is k-fold cross validation. So let's not focus on this for now, because this is just cross validation of metrics like accuracy, so that sometimes when we directly calculate accuracy, it might not be more reliable. So we must, so k-fold cross validation is just so that accuracy is more reliable even in an imbalanced data set. So simply we first initialize the model. It is not actually the training process. We use logistic regression model equals to logistic regression max iteration 1000. So okay, this is the most important part to be noted on how logistic regression model is actually being trained internally. So basically, first of all, we have a current weight, or say initial weight. Those are random weights in a weight vector. So this flowchart clearly explains everything. So let's see. So our tweet, let's say tweet 1 is a vector of 5,000 elements. As I've said you here, this is a vector of 5,000 elements. After we have vectorized it, right? So this is our vector of 5,000 elements, and times weight. Weight is also a vector of 5,000 elements. Now gets multiplied. Obviously they can be multiplied, and the final result, which is again 5,000, which is again a vector of 5,000 elements, is passed through a function called sigmoid function, which is the activation function. There are multiple activation functions like ReLU and sigmoid function itself. So what does this sigmoid function does? What does this sigmoid function do is it generates, it takes the vector and results a value between 0 and 1, which is a probability value, which is a S-curve. You know, it looks like this, S-curve, which is, this is a middle value, and this is the extreme value, which is tending to infinity, and this is tending to 0. Simply you can understand this more by yourself, which is a simple function. This is a activation function. These are called activation functions, and this is 0.5, this is 1, and this is 0. But sigmoid function never actually results 0 or 1, exactly 0 or 1. It just tends to be 0 or 1. Okay, so sigmoid function gives a probability value. So and the formula of sigmoid, and the formula for sigmoid function is also very simple, which is 1 over 1 plus e to the power minus y. And now this gives the sigmoid function gives a probability value which tells positive or negative. If it's closer to 0, it is negative. If it's closer to 1, it is positive. Simple as that. So this is so same happens with tweet 2. It is a vector of 5000 elements, gets multiplied with the current weights in the first iteration. Okay, in the first iteration gets multiplied with the current weights, and the result is passed through sigmoid function, and it gives a probability value between 0 and 1, which predicts whether it is negative or positive tweets. Okay, it's just a prediction. Now there will be errors. Okay, now calculate the error. So watch this very carefully. So by giving error on its prediction, the model learns. This is how the model learns. Okay, so tweet 1 error 0.27, actual was 1 from the data frame of y, we can see that, and predicted was 0.73. so the error of tweet 1 is this much, error of tweet 2 is this much, error of tweet 3 is this much, and so on, of all the 20,000 errors. Okay, 20,000 errors. And remember this, always remember this data frame: 5,000 rows, 5,000 columns, and 20,000 rows of tweets. And the features, these are called terms, and these are documents. The tf-idf vectorizer does this, and so we can see here average all errors equals to one loss value, that is 0.38. so in one iteration, one average loss is calculated. Okay, and then gradient descent adjusts all 5,000 weights at once. So gradient descent comes from calculus, finding out slope from any given curve, especially the concave ones, because the curves which do not have concavity does not actually work, which is a different mathematical problem to talk about. So gradient descent adjusts all 5,000 weights at once. So what does gradient descent? So basically, for our logistic regression problem, we get a simple concave curve like this, which is a very basic thing. So which is very easy to deal with. But in some other higher data science tasks and complex analysis, there will be much more complex patterns like this, and we have to find the minimum position using other gradient descents like stochastic with learning routines, or other optimizers might be needed. But for now it's simple. So we can see this we can visualize this as analogous to a hill, and we have to find the lowest point. Lowest point means the point with lowest error. This is a loss function, and we have to find the minimum loss for this. So the gradient descent tells you where should you move to notch the weights. Where should you notch the weights to decrease your overall error? So the gradient descent optimizes, adjusts the weights again, and the next iteration happens. Now the weights are not random. These are the weights adjusted by gradient descent already in our second iteration, and again the updated adjusted weights get multiplied with the tweets. Same tweets again, same 8,000 tweets. 8,000 tweets. Gets multiplied with all the tweets. Actually it's not 8,000, it's 16,000. Okay, with all our the 80% tweets we have. And again, error is calculated for each, and every error is also calculated, and the gradient descent adjusts the weights so that the error is minimum, so the error gets minimum. So what gradient descent is doing is trying to hit the lowest of the loss function with the minimum error to get the minimum error. So max iteration 1000 means, so this iteration stops either of two ways. One is tolerance value. First is tolerance value. Tolerance value is preset in sklearn as equal to 0.001, or we can manually set it from here. So what that means is after each iteration, if the overall error is not being improved by more than 0.001, then stop the iteration. Yeah, simple as that. So tolerance value is that. Another way the iteration would stop is, hitting the max iteration limit. So you will get a warning, something like saying something like convergence warning, max iteration reached. you would get warning saying something like convergence warning, max iteration reached, or something like that, if the max iteration ever reaches, but generally it doesn't. So careful cross validation is simply, we can talk about it later on. Simply it is simply splitting our training data into multiple folds and using each fold as for testing purpose or for validating purpose, so that we get much more reliable metrics of our model. So now we have trained our model, or have we? Train test split भयो, K4 model initialized. So we have only initialized the model. Now it's time to actually train using the .fit method here. Xtrain and ytrain, these splitted, these are the splitted data. This is the target or cell level, and this is the actual tweets, vectorized tweets. So this line trains the logistic regression model, and we predict this on our test data, that is 20% of our data, that is X test. And we do this because we need to see how our model is behaving, how capable is our model. So because we must, in any data science task, it is must to know how your model performs in unseen data, in the data that that model has not seen before and not been trained on. That is the main purpose of creating an ML model, right? So we create our classification report, which has precision, recall, F1 score, and accuracy and everything. So we can see that our accuracy of our model is 0.73, which is 73%, which is very decent for this model of this size. Definitely okay. So what does this exactly mean and signifies? We can talk about it later on, or you can source it by yourself. Okay, so now this, so in another cell I have trained naive Bayes model, same as that, initialized and fit, which is actually training process, and classification report, and we can see accuracy is very similar. But now we are not going into the depth of how naive Bayes models work. And finally, very important is we use joblib is so very important is saving the model. Joblib is a library of Python which we will be using to store our trained model, so that every time we need the model, we should not rerun this entire cell every time. So we can save the model using joblib.dump and the location you want to save it in. So I have saved every 3 models here, and also save the vectorizer because so what does these saved models have? So these models get saved as .pkl. I can show you here in my Google Drive. The models is saved as .pkl, and the vectorizer is also saved as .pkl, but the NN model gets saved as .s5 because we used a different library called keras here, and the .pkl is provided by the sklearn library. No worries on that. So this .pkl file, or say pickle files, contains the final weights final adjusted weights that we end up with after multiple iterations. And what does our vectorizer contain? Vectorizer contains the vocabulary of the 5,000 words here, the 5,000 features or 5,000 words we have. So it contains the vocabulary and their position, so that all the results are reproducible. So vectorizer should also be saved, otherwise we must again fit and transform like we did earlier. So we save the model, and now in another notebook, just to mount your drive again, we must clean the text again, okay? So that we must, so what I'm doing here is I am giving my own words or own tweets, own sentences, and the model will predict either it is positive or negative. Okay, now let's go. First mount your Google Drive, and then we must create this cleaning function. First import these things, create the cleaning function, and then load your models here. Load logistic regression model from joblib.load from your drive location. Create the cleaning function just like we did earlier, and then also import your vectorizer and vectorize your tweets or text. So this is a function. So finally I created a function intro sentence predict sentiment user. So finally I created a function that takes user input and then runs through this function, through this cleaning function, and then vectorization, and then actually passes this through the model, the pickle model with the adjusted weights, so that it gives so what happens actually is, when I type any sentence, it goes through the adjusted weights. It gets multiplied with the adjusted weights, and the result is then passed through activation function, which is our sigmoid function, and the result is 0 or between 0 or 1, and whichever, and either it is, and based on which value is, and based on how closer the value is to 0 or 1, the target is predicted to be positive or negative. So let's run this for now and see how our model works. So let's try this with a sentence. I love this movie, and let's see how it predicts. And so what is this? This is a confidence score. And these are the other models, and you can see how they perform. And in my project here, the NN is a little bit overfitting due to the, it's the limitation of tf-idf vectorizer. There are other various ways to vectorize and clean text which improves the model performance, but the basic for understanding are those. So don't worry, we will also walk through the other nltk methods and other LSTM or word embeddings techniques for better accuracy of the models. Okay, let's try with other sentences, like so let's input some neutral words like something like meaningless words. Then we get 50% confidence, which around 50% confidence, which means they have not seen the word before. And some sarcastic like I used to love this is actually a negative sentiment. So but the logistic regression predicts as positive because it treats every individual words. For in logistic regression, the context of words does not matter much. Individual word only care about the individual words. Naive is also the same, so it does that. But ANN actually learns the context of the words as well. The hidden layers somehow launch the context of words. They learn the pattern of patterns and actually gives you a good response here. And we can try other like I hate this or something like this, and we get our negative with a very good confidence score. But getting 100% confidence is not good because it's overfitting. So thank you for now, and meet you in another video on and we can talk more about